Hello everyone and welcome to lecture 5 of SE5014, the inorganic chemistry course. We don't have that much material left to cover. We're still making our way through the periodic table by group. I teach the last two groups together, so we are kind of reaching the end of my part of the course, really. Sort of 3 more lectures to go, and then we'll have a revision lecture. So we move on to group 15 then: nitrogen, phosphorus, arsenic, antimony, bismuth, and moscovium. And the main kind of difference between this group and the previous groups that we've discovered is now that we've moved to a very covalent region of the periodic table. So now nearly all of the chemistry of the compounds involved in this group are covalent in nature. And indeed, the chemistry of the first two members of the group, so nitrogen and phosphorus, is far more developed than it is for arsenic, antimony, bismuth, and moscovium. Again, is one of those funny elements that we don't really know that much about. So we tend to focus discussions on the chemistry of nitrogen and phosphorus, and of course nitrogen makes up the overwhelming component of the air we breathe, so we know a fair amount about its chemistry. Moscovium then, element number 115, is an artificial element. It was named and its existence was confirmed in 2015 by UPAC. It has a half-life of 220 milliseconds, or its most stable isotope, moscovium-289, has a half-life of 220 milliseconds. So it doesn't really give us much time to study any of the properties of moscovium. Of course, we assume that it will be in line with the rest of the group, but we can't confirm that. So again, these heavy elements that are found at the bottom of the P block, we tend to omit them in our discussions because we don't know anything about them. Now you can see the natural abundances of the elements from this group in the Earth's crust. Nitrogen and phosphorus are the most naturally occurring in the Earth's crust. We know that nitrogen makes up, as molecular nitrogen, N2, makes up about 78% of the Earth's atmosphere. So the overwhelming component of the air we breathe is molecular nitrogen. And of course, phosphorus then is very important in plant and animal tissue. So it's very important in our bones and teeth. Calcium phosphoapatite makes up the structures of our bones and teeth. And on a molecular level, it's very important to the proteins, in particular DNA, that is obviously the basis of life. So the first two elements really are quite important members of the group in terms of our own human existence. And talking about phosphoapatites, phosphorus occurs naturally, and this is why it's so abundant, because it occurs naturally in these calcium phosphoapatite structures, and you can find it in North Africa, North America, Asia, and the Middle East. And you can see the hydroxyapatite structure there on the bottom right. Now, whilst we talk about phosphorus as being an important element for the basis of life, DNA and plant and animal tissue and that kind of thing, some of the chemistry that has been developed surrounding phosphorus is also used for negative means as well. And there are a series of nerve agents that contain phosphorus. So in the sort of second half of the 20th century, these organophosphate nerve agents were used and deployed. And we see in the news all the time, about the potential stockpiling of these nerve agents, these kinds of nerve agents, and from certain states, and indeed their deployment against their own citizens. And they were developed, for that, as a deterrent against acts of terror and war. And you can see the general structure there is a central phosphate atom, which is bound to various different groups. But the key theme is that there is always some kind of organic group that's bound to a phosphate-like group. And the molecule on the left there is sarin. Now, these were formerly banned in the late 90s, and it was the Chemical Weapons Convention banned any development and or stockpiling of these drugs. And countries were ordered to destroy stock and production facilities. But there has been a recent news story surrounding VX, which is the molecule you see on the right-hand side there. So the organophosphorus nerve agent that has a kind of nitrogen-based organic group. And the organic nature of these things is part of their danger, because it makes them very easily absorbed in the body. So the molecule on the right is VX, and despite a ban on this in the late 90s, there is a recent story surrounding this. And some of you may remember that 3 years ago in 2017, Kim Jong-nam was found dead, and it was suspected that he was poisoned, and he was a relative of the North Korean leader. And this particular nerve agent, VX, an organophosphorus nerve agent, was implicated in his death. Now, one of the really dangerous things about nerve agents is that from a chemical perspective, they're very, very difficult to get rid of. You can treat something like sarin with a room temperature hydrolysis reaction. You treat it with Na2CO3, and you gain the sodium salt of your aqueous organophosphate. So you can see it replaces that fluorine group for an oxygen group or sodium salt. And that's good, because once you create that sodium salt, suddenly you get some charge into the molecule and it becomes soluble, and it becomes much easier to deal with then after it's undergone one of these room temperature hydrolysis reactions. VX is much more difficult to get rid of because it's difficult to hydrolyze, and it only reacts slowly with sodium hydroxide at room temperature. So you have to actually treat it at very high temperatures for a number of hours in aqueous sodium hydroxide in order to attempt to get rid of it. And that reaction proceeds via two routes. The major product cleaves that sulfur carbon bond and essentially splits the molecule, the original VX molecule, into two. But the issue is that the minor product is extremely toxic. So whilst you've solved the problem in some respects, you've also created one, because the minor product of your reaction is likely to be even more toxic than the original VX molecule you started with. Okay. Arsenic is the next one then after phosphorus, and it occurs in elemental form. There are some commercial sources. Antimony SB is very rare and only available in essentially one commercial ore, stibnite. And bismuth occurs elementally, and you can find ores of bismuth. But again, the chemistry of these things isn't really that developed. And I mean, everyone can think of an application of arsenic, right? We can all think of arsenic as a poison. It's also a very important metal biologically in very small concentrations, but we can all think of applications for arsenic. It's much more difficult to think about applications for antimony and bismuth, and whilst they've got applications, in sort of emerging fields of solid state physics, it's difficult to think of any wide-reaching applications, and that's largely because the chemistry of these elements is relatively still undeveloped in comparison to the elements that we've been studying. Okay, so back to a consideration of some of the chemistries of nitrogen and phosphorus. Atomic nitrogen, so nitrogen on its own, is very reactive, but we know that it doesn't tend to occur on its own. It usually buddies up with another nitrogen atom, and we find it as molecular nitrogen, or dinitrogen, N2, which is a pretty stable molecule. It's a pretty happy molecule. It's quite unreactive, actually. It will combine very slowly with lithium at ambient temperatures. When heated, it will react with most group 2 metals and things like aluminium, silicon, and germanium as well. And we've also seen, we studied this in some detail last year when we looked at transition metal complexes. We saw possibly some strange ligands with dinitrogen in them, and they make quite good ligands, and they bond to metals like ruthenium. And you can see an example of a ruthenium, an octahedral ruthenium complex there, which contains one of these dinitrogen ligands. Phosphorus is a really interesting one because it's got a complicated allotropy. That is, it has 12 different forms that have been reported. A reminder then that allotropy is kind of same formula but different crystal structure. There are some key forms of phosphorus. So white phosphorus is a crystalline structure of tetrahedral P4 units, and you can see there that it's got very defined phosphorus-phosphorus bond distances. And we define white phosphorus as the standard state of the element, but interestingly, it's not the most thermodynamically stable form of phosphorus. If you were to heat white phosphorus under an inert atmosphere, so a nitrogen or a helium atmosphere at high temperatures, around 540 Kelvin, then you get another form of phosphorus, red phosphorus. And this consists of these interlocking chains. You can see a picture of it there on the left. And these chains lie parallel to each other in a the non-bonded chains lie parallel to each other. And interestingly, there's a scene in Breaking Bad. Anybody who's seen the series Breaking Bad will remember a scene where Walt and Jesse, I think, are being held captive in a caravan and being asked to, synthesize crystal meth by drug lords. And to get out of it, Walt decides to take red phosphorus that he's using in his crystal meth synthesis and throw it into water, and it creates this huge explosion, and this colourful gas evolves from his actions. And they exit the caravan, and as they're walking off, Walt says that when you throw red phosphine into water, when you throw red phosphorus into water, you get phosphine gas. Now, that is an example of what I call Breaking Bad chemistry, because red phosphorus does not react with water to produce phosphine gas. It reacts with hydrogen to produce phosphine gas, but it would not react with water. So don't believe everything you see in Breaking Bad. Now, if you were to heat white phosphorus at high pressure now, then you obtain black phosphorus. And this is in fact the most stable allotrope of phosphorus. And interestingly, its appearance and electrical conductivity resemble those of graphite. So there's an interesting idea. We speak all the time about graphite and its, potential benefit as a wonder material, and how it's solving lots of things, in the optoelectronic industry and in fuel cells and that kind of thing, as membranes for fuel cells. But we don't often consider whether or not there are other elements in the periodic table that may adopt similar structures and therefore have these layers of delocalized electrons that ultimately yield very high conductivities. And it turns out that phosphorus, black phosphorus in particular, is able to do that, and it has these layered structures which are composed of 6-membered rings, and it has this highly conductive nature because of these reasons, and for the exact same reasons that graphite has this very high conductivity. So we can expect layers of delocalized electrons in these phosphorus type structures as well. And black phosphorus is picking up in terms of research. There's now a lot of research going into black phosphorus and the quest for whether or not it can be applied in the same situations as graphene. Problem is, as graphite. Problem is, it's a little bit more difficult to make because you have to heat white phosphorus under high pressures. So there's an inherent cost to that. Heating anything under high pressure is expensive. So there's an economic impact of that, whereas graphite is readily available. Arsenic, antimony and bismuth are all grey solids, and they all have these layered structures. Each layer contains a 6-membered ring in that chair conformation that you see there. Now, each of the group 15 elements will form a trihydride, so I put the generic formula there as EH3, where E stands for element, and it could be any of the group 15 members. But there's something that's quite interesting if you look at the properties of all of their trihydrides. So I show you a table there of the trihydride for each element and some of the properties. And you can see that there's a large variation in boiling point at ammonia. So broadly, if you go from phosphine through to bismuthane, the boiling point increases fairly regularly. But you'll note that the first trihydride, ammonia, has an abnormally high boiling point at 240 Kelvin. Now, if you were to compare that with the boiling point for the group 14 hydride, so carbon's group, then you can see that as you go down the group, the boiling points increase up to 0. Methane has a boiling point of about minus 160 degrees Celsius. The tetrahydride of lead has a boiling point of about minus 20 degrees Celsius. That's quite easily explained because the molecules are getting larger. Lead has many more electrons than carbon does, and therefore the van der Waals forces that lead to attractive forces within the gas are greater, and those attractive forces yield greater boiling points. And at this point in the periodic table then, from group 15 onwards, if you were to repeat that exercise with the hydrides of these groups, so group 15, 16 and 17, then you see something odd, and boiling points don't simply increase as you go down the group for the trihydrides, but the boiling point of the hydride with the first element of the group, so we're talking about nitrogen, but this also applies to group 6 and 7, you find that the boiling point of that first hydride is abnormally high, and after that the boiling point increases. And you can see that it's not slightly higher. The boiling point of the first hydride in the group is significantly higher than the second one. So there must be something else going on, and we'll focus on ammonia, or NH3, because we're talking about group 15. We know that there must be additional intermolecular forces of attraction. It can't just be these kind of van der Waals forces. And the result is hydrogen bonding, and you know all about the hydrogen bonding in polar molecules like water. That's why water has such a high boiling point relative to the rest of group 16, or the hydrides of group 16. And exactly the same is true for ammonia. So you get an interaction between the lone pair, the huge lone pair on nitrogen, and the partial positive charge that's found on the hydrogen of another ammonia molecule. And again, this is why, I mean, we can take this right back to the very first lecture that we spoke about when we were looking at dissolving sodium in liquid ammonia. These exact properties of ammonia actually mean that that stable cavity that exists between the electron and ammonia. So the only reason that when we put sodium into liquid ammonia and it gives up its valence electron, so we get Na plus and that single electron in solution, what happens is that a cavity is formed around that electron, and it means that quantum mechanically, at least, that electron is stable. Well, part of the reason why it does that is because of a hydrogen bonded network that exists within the ammonia solvent, and the fact that it's able to form a stable cavity through interactions between ammonia molecules, but also through interactions between the ammonia molecules and the negatively charged electron and the positively charged sodium ion. Now, the first element of the group stands apart because it forms oxides in which pi bonding plays a role. So you can see the structure of various oxides of nitrogen there. You can prepare dinitrogen monoxide by decomposition of solid ammonium nitrate. You can either heat it at high temperatures, around 500 Kelvin, or you can do it in aqueous solution, and you tend to get a much purer product if you do it in aqueous solution. It has a faint sweet odour, and it will dissolve in water to give a neutral solution that is quite unreactive. So due to that, you can posit that equilibrium in that reaction when you dissolve N2O in water will lie very far to the left. We spoke last year about VSEPR theory and resonance. The molecule itself is linear and is best represented by the left-hand structure. Although what's really interesting is that if you were to take some measurements of the bond lengths of the nitrogen-nitrogen and nitrogen-oxygen bond lengths, you find that the nitrogen-nitrogen bond is about 113 picometers, and the nitrogen-oxygen bond is about 119 picometers. So whilst we represent that on a page by the left-hand structure, the bond lengths themselves would actually suggest that a triple bond exists between the two nitrogens and a single bond between the oxygen and the nitrogen. Nitrogen monoxide then can be made industrially from ammonia. You need high temperatures and an expensive platinum catalyst for that. And nitrogen monoxide has an important role in biology. And the winners of the 1998 Nobel Prize in Physiology and Medicine were awarded so because of their discovery relating to the presence of nitrogen oxide and its ability to act as a signaling molecule in the cardiovascular system. And you can see there a scheme of the role of nitrogen monoxide and its synthesis in vivo from the amino acid L-arginine, and it's then and this is catalyzed by nitrogen monoxide synthase enzymes. You can read some papers there if you're interested. Dinitrogen trioxide, then N2O3, you can get that as a dark blue liquid. And dinitrogen tetraoxide and nitrogen dioxide exist in equilibrium. So we tend to discuss these things together. So you can see the equilibrium set up between the two molecules here. The solid is a colourless and diamagnetic solid that's consistent with only the presence of N2O4. As you start to heat the solid, then you start to get the evolution of a brown vapour, and at 294 Kelvin that contains about 15% nitrogen dioxide. So you're shifting equilibrium to the right as you heat up the substance. That vapour darkens yet still as you raise the temperature, and at 413 Kelvin the dissociation of N2O4 is almost complete, and you've got almost pure NO2. Heat it up even further and you get the complete dissociation of nitrogen and molecular oxygen. There's a good video on this equilibrium on the YouTube channel that I show you here, so I'd urge you to watch that. Now you can see that nitrogen forms a range of oxides, quite an extensive range of oxides. For the rest of the group, you only get two oxides. So you only get E2O3 and E2O5, where E is the element bismuth, phosphorus down to bismuth. And they can also dimerize. So you can also get E406 and E410, but the core structures that the rest of group 15 will only form two oxides, unlike nitrogen. So nitrogen's the odd one out, really. Nitrogen and phosphorus will form a range of acidic compounds. So you can see nitrogen forms many oxoacids, some of which are important in the chemistry laboratory. And similarly, oxoacids of phosphorus are many, and they're important in the chemistry laboratory. You might recognize some of these as buffer reagents. They can be used to control pH. They're also important from a biological perspective. And of course, phosphates are very important for biological systems. So DNA, RNA, and phosphate esters are all very important biologically. Of course, our cell membranes themselves are composed of phospholipids. These are sort of phosphate esters that are bound to long hydrocarbon-based lipid tails, and indeed our bones and teeth are constructed from collagen and single crystals of hydroxyapatite. And you can see there that I pose a question, why do we put fluoride in drinking water and why do we put fluoride in toothpaste? Well, have a look at that image there. That's a tooth with some plaque on it. And that plaque acid enters the rods in teeth and it breaks down enamel. And if it breaks down enamel, then more acid can get in and decay or rot the tooth. But fluoride is able to enter those rods in the tooth and essentially repair those enamel lesions or remineralize those enamel lesions. And it does so because of the inherent chemistry of hydroxyapatite. So you can see there that fluorine is able to enter hydroxyapatite and replace that OH group and remineralize the hydroxyapatite, essentially repair the corroded enamel. Okay, I will leave it there. A couple of questions for you, and I will see you in the next session. Thank you.